All right, in part 9, we are going to be looking at some applications. And so this means word problems. And I know sometimes students can feel a bit hesitant about working with word problems. Hopefully, I can make these very accessible and easy to follow. If you can follow these patterns, the math that we're doing in these problems is actually quite a bit easier than the other math we've been doing. There's no or very minimal quadratic equations. It's really pretty basic equations you're going to be solving. The hard part is setting up the equation from the word problem. So hopefully I can break it down pretty simple and have some patterns that you guys are able to follow easily. This first example is giving us a three-dimensional shape that we're going to try and find the volume for. Now we're not going to be actually finding a number for the volume. We're going to be writing an expression for the volume. And this is not a regular shape. This is not like a cube or something that we know the formula for the volume of. What we're going to need to do is break this into two pieces. So if you can imagine looking at this top small piece and the bottom bigger, flatter piece here. Now this rectangular prism is technically what it's called. If I wanted to find the volume of that shape, that would be length times width times height. So I know the length, I know the width, I know the height. So for the bottom piece, that would be x times x plus 6 times 3x plus 4. And then I need to find the volume of the top piece. Okay. So in doing the top piece, I know the height is x, and I know whatever this length is, x plus 6, this length will be the same, this length will be the same, and this length will be the same. So I know this piece here, but what I don't know is how wide that piece is. But I know this whole piece is 3x plus 4. I know this little part of it is x. And I know this little part of it is x. And what I want to find is this middle piece here. Well, if the whole thing is 3x plus 4, and I take off an x, and I take off an x, then 3x plus 4 minus x is x plus 4. So this piece right here is x plus 4. Well, now I know this is x plus 6, and I know the height. So the top piece is x times x plus 4 times x plus 6. And this just requires us to use either FOIL or the box method, whichever you prefer. So for the bottom piece, 3x plus 4 times x plus 6, that's going to give me 3x squared. And 18 and 4 is 22x and plus 24. And then distributing the x, that'll give me 3x cubed plus 22x squared plus 24x. And then the top piece, x, and then x plus 4 times x plus 6 is x squared plus 10x plus 24. Distributing the x, that gives me x cubed plus 10x squared plus 24x. So then combining those like terms, 3x cubed and 1x cubed gives me 4x cubed. 22x squared and 10x squared gives me 32x squared. And then 24x and 24x is 48x. All right, so that's our answer for that first one. The next type of problem we're going to be looking at is called a work problem. And work problems are pretty standard in how they are going to give them to you. There's not a lot of variation. So typically we're looking at a scenario where we have the rate of one person plus the rate of a second person, and then talking about the rate together that they're completing a single job. We could change this to where we have, instead of 1 and 2 people, we could have 1, 2, and 3 people, and then they're right together. Not a ton of ways for us to vary this problem. So first we want to look at the rate of the first person, second person, and then their rate together. 2 of these will be given, and then you'll be trying to find the third one. Sometimes we know the first person and the second person, we're trying to find their rate together. Sometimes we know one person and then their together rate and trying to find the second person's rate. It's not a lot of variation here. So the example we're looking at here, it says Bob paints the living room by himself and it takes 5 hours. So Bob, 5 hours. And Jan paints the same living room in 3 hours. How long will it take them to paint the living room together? So I'll use T for together, and we don't know. So we have Bob's rate, Jan's rate, and we want to find their rate together. That'll be 1/5. They're painting 1 living room in 5 hours for Bob. Jan does it 1 living room in 3 hours. We want to find out how long it would take them to paint 1 living room together. So I have 3 denominators here. The common denominator among all 3 would be 15t. And I'm going to multiply both sides of the equation by that. Well, 15t divided by 5 would be 3t. 15t divided by 3 would be 5t. And then here the t's cancel and it's equal to 15. So that gives me 8t equals 15. T is equal to 15/8. And if you were to calculate that out, that would be a little bit less than 2, 1.875 hours. Now, if you think about this, sometimes what I'll have students do is like, oh, if it takes him 5 hours and it takes her 3 hours, then it'll be the average of the 2. Together, it'll take them 4 hours. Well, that doesn't make sense, because if she can do this by herself in 3 hours, having Bob's help would make it even faster. So it makes sense that their together rate should be faster than the fastest person. So you should be expecting to get a number here less than 3. Now the next type of word problem we're going to look at is called a distance rate time problem. And this is probably one of the more common problems. In fact, I know we will see this again towards the end of this semester. And we'll be doing this type of problem again. So what we know from physics, very basic physics, is that distance is equal to a rate or speed times the amount of time traveling that speed. So for example, I always think of like those memes or GIFs you see on social media where you've got, or videos or whatever, where you've got somebody, or 2 people driving in a car and one of them is like, so if we're driving 60 miles per hour, how long will it take us to go 60 miles? And the other person is supposed to be acting kind of dumb or whatever, and it's like, I don't know, how long will it take us to go 60 miles? Maybe 2 hours or something like that. Well, if you're going 60 miles per 1 hour, it'll be 1 hour and you'll travel 60 miles. Now, obviously when we drive, our speeds fluctuate, but if we're talking about a constant speed at, traveling the exact same speed the whole time, that's the relationship we can use here. Distance is equal to rate, or your speed, times time. So we're going to be making a chart to organize the information in the problem, and then we're going to be using this relationship to write an equation. So I'm going to go ahead and set up our chart here, and what we're going to be using is the fact that rate times time is equal to distance. So it says Sam and Alex are going down a river in their boat. Their trip downriver, meaning with the current, so we have a trip with the current. If you've ever been in a river, you know going with the current is a lot easier than going against the current. Takes 6 hours. Their trip back up the river to where they started, so that means they're going the same distance. If they have a river here and they're going down the river and then they're going back up to where they started, that's the same distance there and back. Let's see. Their trip back up the river to where they started takes 10 hours. So going against current. So if you think about that again, going with the current is the easier trip. Going against the current, fighting against the current, should take longer. It's harder work. And it says the distance they traveled in total was 60 miles. So that means they went 30 this way and 30 this way. So this trip took 30 and this trip was 30 miles. It says find the rate of the current and the speed of the boat in still water. Now we haven't written anything here yet, but those two pieces they told us we're going to find is what our variables are going to be. So I'm going to let x be the rate, the speed of the boat. In still water. I'm going to let y be the current. Now just thinking about this scenario here, if they're going down the river or if they're going up against the river, they need to be traveling faster than the current, because when they travel back upstream and they're fighting against the current, if the current is faster than them, they'd be moving backwards, not forwards. So they have to be going faster than the current, or their speed in still water has to be faster than the current. So with the current means they have the speed of their boat, or of their boat, plus the current pushing them. Going against the current, they have the speed of their boat minus the current slowing them down. Now again, rate times time is equal to distance. So I have my rate times my time equal to my distance. 6 times x plus y equals 30. And then here, 10 times x minus y is equal to 30. Now, so often with problems like this, when it's set up like this, I see students just immediately distribute, and that's actually not what's easiest here. Rather than distributing, what I'm actually going to do is divide both sides by 6 to get rid of that 6. Dividing by 6 here, that'll be gone. 30 divided by 6 is 5. And here, dividing both sides by 10, I have x minus y is equal to 3. This is a system of equations, and the way we can solve it is by adding the equations together. X plus x is 2x. Positive y, negative y cancel out. 5 plus 3 is 8. Dividing both sides by 2, x equals 4. But remember, it's really important to write down what your variables represent because it's easy to forget. X is equal to 4, and x is the speed of the boat in still water. So the boat is going 4 miles per hour. And the current, well, if x plus y is equal to 5, and x is 4, 4 plus what equals 5? Well, 4 plus 1. So the current is 1 mile per hour. All right, the next type of example we're going to look at is using proportions. It says set up proportions using, use words first can be helpful and then solve. First example says the monthly loan payment for a car is $28.35 for each $1,000 borrowed. At this rate, find the monthly payment for a $6,000 car loan. So if it's $28.35 per 1,000, and we have a $6,000 car loan, and we want to find what would the monthly loan payment be, we can go ahead and cross multiply. 1,000 x is equal to 6,000 times 28.35. If I divide both sides by 1,000, I get x is equal to 6 times 28.35, which is $170.10. And that's it. Okay, we've got two more examples talking about simple interest and mixture problems. And the setup for these two scenarios here is very similar. We're going to be, again, making a chart kind of like we did with the distance, rate, time problems. So Again, we're going to set up a table with the given information, and then we're going to write equations from those charts. So, in the first example, it says Laura borrowed a total of $22,000 from 2 separate banks to start a business. One bank charged the equivalent of 4% simple interest, and the other charged 5.5% interest. If the total interest after 1 year was $910, determine the amount borrowed from each bank. Now, if you read that whole thing all at once, it feels overwhelming, and it kind of feels like, oh, I'm not even going to try this one, let's skip it. Well, you're going to have multiple word problems on your quizzes and exams, so you don't want to skip all of those, and like I said, a lot of times the math you're doing is actually easier. So let's just make a chart of the information that we were given. We had the first bank and the second bank. Now, our amount borrowed is one piece of information we're going to look at. Let's first just say the interest rate. So the first one charged a 4% interest rate, and the second one charged a 5.5% interest rate. Let's go ahead and write those as a decimal. So I'm going to write interest rate, IR, as a decimal. And that's going to be 0.04 and 0.055. And we don't know how much was borrowed from each bank. We know she borrowed a total of $22,000, but we don't know, excuse me, how much from each bank. So let's just say the amount borrowed and let's just say X from the first bank. We don't know how much, but we know that the total will be $22,000. So however much she borrowed from this bank, it would be $22,000 minus X. That would be what's left for what she borrowed from the second bank. So we have, so far, our interest rate is a decimal times the amount borrowed. And if I multiply those, that's going to be the interest amount. Or the amount of interest we have. So 0.04x and 0.055 times 22,000 minus x. And we know that the total amount of interest after 1 year was $910. So the amount of interest from this bank plus the amount of interest from this bank is going to equal $910. So we can write an equation for that. 0.04x plus 0.055 times 22,000 minus x is going to equal 910. And now we have an equation with just x's that we can go ahead and solve. Now, we could go ahead and distribute the 0.055 here, and distributing that, we get 0.04x plus 1,210 minus 0.055x equals 910. 0.04x plus, minus 0.055x gives me negative 0.015, and you can be using a calculator to help you do these decimal calculations. Subtracting 1210 from both sides, I get negative 300. Dividing both sides by negative 0.015, we get x is equal to 20,000. So that means I borrowed, or she borrowed, 20,000 from the first bank, and that leaves 2,000 left from the second bank. So the first bank, she borrowed 20,000, and the second bank, she borrowed 2,000. Okay. One more example, and then that'll be the end of our application problems for this section. The next one is a mixture problem talking about a nurse mixing saline solution. You don't need to know anything about saline solution or how all of that works to be able to do this problem. It's a very similar setup to what we were just doing. There's just going to be a third line here. So it says a nurse mixes 60 cc's of a 50% saline solution with a 10% saline solution to produce a 25% saline solution. So she has two different kinds. She wants to kind of water down the 50% with the 10%, and how much of the 10% solution should he use. So we're going to make a chart, and there's 3 different percents we're looking at here. We have a 50% solution, we have a 10% solution, and we want to make a 25% solution. So we want to talk about the amount of each solution. So the amount of, and they are using the units cc's. The amount of cc's. Well, it tells us we have 60 cc's of the 50%. So we have 60 of these. We don't know how much of the 10%. It says with a 10%. It doesn't say how much. But however much of this solution plus however much of this solution, that mixed together is what will make the 25% solution. So 60 plus x. Now we have the percentages as a decimal. So we want to write, again, whenever we're working with percentages, we always want to work with them as a decimal. So the percent as a decimal would be 0.5, 0.1, and 0.25. And this tells me how much saline it is. So it's all water and then 50% saline. Here it's all water and 10% saline. We want all water and 25% saline. So if I was to multiply the percent of saline times the total amount of that mixture, that's going to tell me how much saline. So the amount of saline is 0.5 times 60. Well, that's 30. 0.1 times x. And then 0.25 times 60 plus x. And however much saline here plus however much saline here, that mixed together gives me the solution I want. So 30 plus 0.1x is equal to 0.25 times 60 plus x. And then we can go ahead and solve that equation. So solving that equation, distributing the 0.25, we have 30 plus 0.1x is equal to 15 plus 0.25x. Subtracting 15 from both sides and subtracting 0.1x. That cancels and that cancels, and I have 15 is equal to 0.15x. So dividing by 0.15 on both sides, x is equal to 100. Well, again, we want to know what that represents. So x was representing the amount of 10%. And that's exactly what the question asked for. How much of the 10% solution should he use? 100 cc's. And that brings us to the end of our Part 9 video and all of those application questions.